Greetings of the day. I'm Dr. K. Raghuram Mohan Reddy. The course name is Unconventional Machining Process. The topic is Ion Beam Machining. Department of Mechanical Engineering. I'm Dr. K. Raghuram Mohan Reddy. Course name is Unconventional Machining Process. In that, the topic is Ion Beam Machining. So this is the course learning outcome of the today's topic. At the end of this session, student will be able to understand the basic working of ion beam machining. Okay, right. In non-traditional machining processes, usually we have three broad categories: mechanical, thermal, chemical and electrochemical. Under mechanical, we have ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. In chemical and electrochemical, chemical machining, plasma chemical machining, electron chemical machining. In thermal, we have electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. So far we have covered electro discharge machining, electron beam machining, and in the last presentation we have seen laser beam machining. Now we are discussing ion beam machining, which is more or less similar to laser beam machining. However, we'll discuss the different features compared to laser beam machining. How it is different from laser beam machining is the important point. Right. Introduction to ion beam machining. Ion beam machining takes place in a vacuum chamber using charged ions fired from an ion source toward the workpiece by means of an accelerating voltage. Okay, here it is similar as compared to laser beam machining. Okay, so vacuum chamber would be there in laser beam machining too. Okay, right. The mechanism of material removal in ion beam machining differs from that of electron beam machining. So the setup is same, but the mechanism of material removal is different from the electron beam machining. It is closely related to the ejection of atoms from the surface by other ionized atoms, nothing but ions that bombard the work material. So here, instead of impact of laser beam, here the ions will bombard the work material to remove the work material or material removal. Okay, right. The process is therefore called ion etching, ion milling or ion polishing. So here the entire material removal performance will be done by ions. So that's why it is ion etching, ion milling or ion polishing. Okay, right. Now let us see the important components of the ion beam machining. Now look at this figure, ion beam machining. So here cathode, anode aperture, intermediate electrode, controlling electrode, extractor anode, ion beam, electrostatic lens, working chamber, workpiece. This is table where the workpiece is mounted. Next, electron knocked out. This is to vacuum pump to create vacuum. Right. The machining system shown in this figure gives the clarity of ion beam machining system setup, which has an ion source that produces a sufficiently intense beam. Okay, see here, with an acceptable spread in its energy of the removal of atoms from the workpiece surface by impingement of ions. So that's why it is called ion milling or ion polishing or ion etching. So here the ions are impacting the workpiece material to remove the material over the surface of the workpiece material. Okay, right. Now see here, cathode. Okay, that is the starting point of this setup. Okay, and vacuum chamber, that is the important structure in this setup. Okay, a heated tungsten filament, this one, acts as the cathode. Okay, from which electrons are accelerated by means of high voltage, that is 1 kilovolt toward the anode. Okay, a heated tungsten filament acts as the cathode. Okay, so here the cathode material is tungsten. Okay, right. During the passage of these electrons from the cathode toward the anode, they interact with argon atoms in the plasma source to produce argon ions. Okay, so here see this governing equation, let us say Ar plus electrons, so Ar plus 2E. Okay, so here argon ions will be producing with this equation. Okay, right. Now a magnetic field is produced between the cathode and anode that makes the electrons spiral. Okay, so here cathode is a negative one, anode is a positive one. So definitely a magnetic field is produced between the cathode and anode that makes the electrons spiral. Okay, so here the electrons will flow from the cathode to anode. Okay, right. The path length of the electrons is therefore increased through the argon gas, which in turn increases the ionization process. So here ionization process is nothing but delivering the ions continuously from the cathode tungsten filament source. Okay, right. Here the path of the electrons is therefore increased through the argon gas. So here we have to take either helium or argon gas. Okay, so these are the neutral gases, usually we can say neutral gases. Okay, right. And the chamber should be vacuum. Right. The produced ions are then extracted from the plasma toward the workpiece, which is mounted on a water cooled table having a tilting angle of 0 degrees to 80 degrees. Okay, so that is about the tilting position of the table. Next, machining variables such as acceleration voltage, flux and angle of incidence are independently controlled. So what are the machining variables? Acceleration voltage, flux, and angle of incidence. Okay, right. Ion beam machining is an atomic bit machining process which is used to machine a product with high resolution of the order of zero point 0.1 microns. See how accuracy it is. Okay, how accurate. Okay, ions of inert gases like argon with high kinetic energy of the order of 10 keV, that means kilo electron volts, are used to bombard and eject atoms from workpiece surface by elastic collision. Okay, so here the mechanism of material removal is due to elastic collision. Okay, and what could be the kinetic energy of the order 10 kilo electron volts. Okay, next, what are the components of ion beam machining? The main components of ion beam machining are vacuum chamber, voltage source, tungsten cathode filament, plasma source of argon atoms, and finally the lens. Okay, now let me reiterate: vacuum chamber, voltage source, tungsten cathode filament, plasma source of argon atoms, and lens. These are the main components of ion beam machining. Right. Now let us discuss one by one. First one, vacuum chamber. Next, let us discuss the function of each main component and its description. Okay, right. Now let us discuss the function of the vacuum chamber. The vacuum chamber is essential to maintain a low pressure environment to prevent ionized particles from colliding with air molecules. This environment ensures a clean and controlled ion beam for precise machining. So the main function of the vacuum chamber is to create vacuum which must maintain a low pressure environment to prevent ionized particles from colliding with air molecules. Okay, so if there is any sort of pressure, then there would be a chance of colliding these ionized particles with the air molecules. Okay, that it should not happen. Okay, then if there is any deviation, the workpiece material removal will not be as per our expectation. So that's why here we are creating a vacuum environment, okay, for the perfect impacting of the electrons onto the workpiece surface. Okay, right. Let us see the description. It is a sealed enclosure from which air and other gases are removed using vacuum pumps. Okay, so in the entire chamber, there should not be any gas molecules or any air. Okay, so by using vacuum pumps, we are evacuating all these things. Okay, so this creates a space with very low atmospheric pressure, which is necessary for the ion beam to travel without interference from air particles. Already we have discussed. Okay, if there is anything in the vacuum chamber, then we cannot say that it is vacuum chamber. Okay, if there are air particles in the chamber, then definitely there will be a chance of interference. So then definitely the workpiece material removal will not be as per the requirement. Okay, right. Next, voltage source. The voltage source provides the necessary electrical potential to accelerate ions toward the workpiece. Okay, so here voltage source is controlling the acceleration of the ions which are producing from the cathode. Okay, now in ion beam machining, high voltages, typically in the range of several kilovolts, are used to generate and accelerate ions. Okay, so here voltage source will generate and accelerate the ions. The voltage source ensures a consistent and controllable energy input, which is a crucial for the precision of the machining process. Okay, so here the voltage is playing a predominant role in controlling the energy input. Okay, which is very much important in terms of precision of the machining process. So the entire precision of this setup is particularly depending on the voltage source. This is a controlling setup, okay, or controllable energy unit. Next, the first and foremost one is the tungsten cathode filament. Okay, the tungsten cathode filament serves as the electron emitter which is necessary for generating the ion beam. Okay, so here the tungsten cathode filament generates the ion beam. Okay, look at this figure. The topmost one is the cathode. Okay, that is made up of tungsten element. Right. Tungsten is used due to its high melting point and ability to emit electrons efficiently when heated. Okay. So upon heating, the tungsten cathode filament generates the ion beam. Okay. So because of its high melting point and ability to emit electrons efficiently, we are using tungsten as the cathode element. When a current passes through the tungsten filament, it heats up and emits electrons. These electrons ionize the argon gas atoms in the plasma source. Okay, so these electrons ionize the argon gas atoms in the plasma source. Okay, so this is about tungsten cathode filament. Next, plasma source of argon atoms. The function of plasma source of argon atoms is that the plasma source generates argon ions which are then used to form the ion beam. The plasma source of ions, argon ions, which are then used to form the ion beam. Argon gas is introduced into the vacuum chamber and ionized by the electrons emitted from the tungsten cathode filament. Okay, here the argon gas is introduced into the vacuum chamber and ionized by the electrons emitted from the tungsten cathode filament. Here we should make a note that here the gas is inert argon gas. Okay, we cannot use any other gases in this vacuum chamber. Okay, if we use any other gas, our purpose will be wasted. Right. This ionization process creates a plasma, a state of matter consisting of free electrons and ions. Argon is chosen because it is inert and does not react with the workpiece material. So just we have discussed that one. If we use any other gas other than inert gas, what will happen? It will react with the workpiece material. Okay, so that's why we are using inert gas, particularly argon here. Okay, Right. Next, lens. The function of lens. The lens focuses and directs the ion beam onto the specific area of the workpiece that needs to be machined. So as per our required profile, the lens is controlling the path to be machined on the workpiece. Right. The lens in ion beam machining is typically an electrostatic or magnetic lens that precisely controls the path and focus of the ion beam. Just we have discussed one. Okay. So whatever the path, whatever the profile that we want, so based on that, we have to deflect the lens in this setup. Okay. By adjusting the lens, the beam can be directed with high precision to achieve the desired machining effect. Okay. So we have to adjust and deflect the lens in order to have the control and directed beam onto the workpiece material to cut or to machine on the workpiece. Right. Now let us discuss working principle. First one, vacuum creation. Preparation. The workpiece is placed inside the vacuum chamber. First we have to keep the workpiece inside the vacuum chamber. That is, the entire setup is with vacuum chamber. However, what we are doing, we are evacuating if there is any gas. Now let us see. Evacuation. Air and other gases are removed from the chamber using vacuum pumps, creating a low pressure environment essential for the ion beam to operate effectively without interference from the air molecules. Okay, so we have to evacuate all the air molecules in order not to collide with these air molecules, so that the evacuation is the important parameter in this working of ion beam machining setup. Next, ion generation. Filament heating. The tungsten cathode filament is heated by passing an electric current through it, causing it to emit electrons. However, through electrical power supply, we are energizing this one so that it delivers the electron beam. Next, plasma formation. Argon gas is introduced into the vacuum chamber. The emitted electrons collide with argon atoms, ionizing them and creating a plasma, that is mixture of free electrons and positively charged argon ions. Okay, so here mixture of free electrons and positively charged argon ions will play a key role for the colliding the workpiece material. Okay, right. Next, ion acceleration. Electric field application. A high voltage is applied between the cathode, that is negative one, and anode, positive, creating a strong electric field. Okay, and ion extraction. The positively charged argon ions are attracted toward the negatively charged cathode and are accelerated through a series of grids or apertures towards the workpiece. Okay, so here the ion extraction is taking place like this. The positively charged argon ions are attracted toward the negatively charged cathode, that means from bottom to top, and accelerated through a series of grids or apertures toward the workpiece. Okay, right. Ion beam focusing and direction. Lens system. The accelerated ion beam is passed through electrostatic or magnetic lenses that focus and direct the beam to a specific precise location on the workpiece. Okay, what the lens system do? The accelerated ion beam is passed through electrostatic or electromagnetic lenses that focus and direct the beam to a specific, precise location on the workpiece. Now, beam control. The lenses and deflection plates ensure the ion beam maintains a tight focus and can be scanned or directed to the desired areas of the workpiece. So here the beam is controlled with these lenses. Okay, so we have to deflect these lenses through the deflection plates to ensure the ion beam maintains a tight focus on the workpiece. Now, material removal. Ion impact. The high energy ions strike the surface of the workpiece, imparting their kinetic energy to the atoms of the workpiece material. So usually when there will be a high impact on the workpiece material by these ions, the material removal will be taking place. Okay. Now what is sputtering? This energy transfer causes atoms from the surface of the workpiece to be ejected, a process known as sputtering. Okay, let me reiterate. The energy transfer causes atoms from the surface of the workpiece to be ejected, a process known as sputtering. Right. The ejected atoms are removed from the chamber by the vacuum system, ensuring a clean machining process. Okay, so constantly the setup releases the ion beam. The ions will strike the workpiece material to remove the material on the surface of the workpiece. Okay, so the ejected atoms are removed from the chamber by the vacuum system. Okay, so always we have to ensure the vacuum environment in the chamber. Right. Machining control. Process parameters. The machining process is controlled by adjusting various parameters such as ion energy, beam current, exposure time, and beam focus. Okay, let us see one more time. The machining process is controlled by adjusting the following parameters. First one is ion energy, beam current, exposure time, and beam focus. Okay, out of all, the ion energy is the important and firstmost one. Next, precision and accuracy. Ion beam machining allows for extremely precise material removal, enabling the creation of intricate and fine features on the workpiece with minimal thermal damage and high surface finish quality. Okay, so here along with the material removal, we should maintain the free of thermal damage. Okay, and there should not be any thermal effect, and also there should not be any heat affected zone nearby the striking over the workpiece material. Okay, in order to have good surface finish or quality. Now let us see the applications. Micro fabrication used in semiconductor manufacturing for precise etching and patterning. Surface modification used to modify surface properties like roughness, reflectivity, and chemical composition. Next, thin film deposition. In conjunction with other techniques, IBM can be used for the deposition of thin films. So, the greatest one from the IBM is that we can deposit very thin films. Okay, right. Advantages of IBM: high precision and accuracy. Okay, fine detailing. Ion beam machining can achieve extremely fine detail and precision, making it suitable for micro and nano fabrication. Okay, this is the greatest advantage of the ion beam machining. Okay, micro and nano level fabrication is possible with the ion beam machining. And one more important one is that minimal damage. The process causes minimal thermal and mechanical damage to the workpiece, preserving the integrity of the material. See, always for any manufacturing process, there should not be any mechanical or thermal damage. There should not be any induced stresses. Okay, so here ion beam machining serve all these advantages. Next, second one, versatility. Wide range of materials. It can be used on a variety of materials including metals, semiconductors, ceramics and polymers. See, few systems or manufacturing processes or material removal process can be limited to a few materials or metals, but here it is a versatile one. We can machine metals, semiconductors, ceramics and polymers. Next, complex geometries. As we all know that in manufacturing system, machining complex shapes through conventional machining is very complex and tedious, and sometimes we cannot achieve. Okay, so thereby we are introducing non-traditional machining process. But out of all the non-traditional machining process, iron beam machining will play a perfect and powerful role towards the complex geometries machining. Okay, right. Surface quality. Smooth surfaces produces very smooth surface finishes, which is essential for optical components and other high precision parts. See, sometimes we need high grade or high level surface finish is required. Okay, particularly for optical components. So this ion beam machining will be the best suited one. Right. As a non-contact process, it leaves no residual stress on the workpiece surface. Okay, there will not be any residual stress because there will not be any direct contact to the workpiece material during the machining process. Fourth one, controlled material removal. Selective etching allows for highly controlled material removal, which is crucial for applications requiring precise depth and feature control. And layer by layer removal can remove material in extremely thin layers, enabling the creation of very thin films and coatings. Okay, so through ion beam machining, we can remove the material layer by layer, very thin layers. Okay, next, applications in advanced technologies, semiconductor industry, optical components, nanotechnology. Now let us see semiconductor industry. Widely used in the semiconductor industry for etching and patterning at the nanoscale. So here in semiconductor industry, we need to machine in a nano level, so it is best suited. Next, optical components, essential for fabrication of high quality optical components like lenses and mirrors. Last one, nanotechnology, important tool in nanotechnology research and development for creating nanoscale devices and structures. Okay, so with this I am concluding this presentation. Thank you very much.
Like, share, and subscribe. Hit the bell icon for more updates.